Today we'll be focusing on chapter gases in this video. So before this, you guys have already learned about matter and what is matter and what are different states of matter. So let's quickly review that before we begin with this chapter. Matter is basically anything that has any mass or that occupies any space. So everything and anything that you can feel, that you see, essentially is matter. Matter can be classified into three different states. One is solid, liquid, gas. You guys have already studied about different properties of some of these properties of solid, liquid, gases. And in this chapter, we will majorly be focusing on different properties of gases and how they are related to each other. So just a quick reminder that solids have the molecules in solid are very closely and compactly packed in each other, around each other, whereas in liquids these molecules have some tiny spaces between them, whereas in case of gas the space between the different molecules of gas is comparatively a lot bigger. And when it comes to their shape, volume, their compressibility, and their ability to flow, solid, liquid, and gases behave different. For instance, solids, they have a fixed shape, they have a fixed volume, they cannot be compressed, and they do not flow. So because there is no space between these molecules in a solid, you can't push and pressurize and compress it. Whereas in case of liquids, liquids have an indefinite shape, meaning they don't have a shape of their own. They will take up the shape of the container they are placed in, but their volume is fixed. So if you're trying to fill up like 2 cups of water into a bottle which can only hold 1 cup, that's not possible. You can't just simply change the volume. You can't simply compress water. So that's why their volume is fixed and they cannot be compressed, but they do flow. They do have the property or ability to flow. Whereas gases, they do not have a specific shape, they do not have a specific volume, they can change their shape depending on the container they are placed in, and same is true for their volume. Since these particles like to be very far apart from each other, whichever container you place them in, the distance between these particles is going to increase and these molecules will spread out throughout the space of the container. So their volume is also indefinite. And because of that reason, it's easy to compress gases. They can be compressed to a smaller volume because there's so much space in between these particles. If we try to compress it, the space basically would decrease and the gas can be compressed. And same is true for their ability to flow. Gases can flow. Now let's talk specifically about gases. So if we think about different properties of gases, they would expand. It's just seeing everything, repeating everything what we just discussed. They can expand to completely fill their container. They take the shape of their container. They have very low density in comparison to solid and liquid state. And that is why, because density, if you remember, is mass over volume. It's the ratio of mass and volume. So gases, basically if you have the same amount or same mass of a substance in solid, liquid or gas state, in gases they are going to occupy less density. Why? Because their mass is same, but gases occupy a much larger volume. So the same mass divided by a much larger volume will give you a smaller density. That is why gases have much lower density in comparison to their solid or liquid form of matter. They can be compressed, they are compressible, and mixture of gases are always homogeneous. For instance, a mixture of gas is air. It consists of a mixture of nitrogen, hydrogen, oxygen, some bunch of other gases. So that mixture is always homogeneous and it's usually fluid, which means it can flow. Moving ahead, if we talk about kinetic molecular theory, that basically is a theory that gives information of how the gas particles behave. It is a theory or it's a model that allows us to understand the behavior of a gas and understand how it would predict how it would behave. So that is given by kinetic molecular theory. There are very few simple points that this theory tells us that helps us explain the characteristics of gases, okay, which are basically that each gas is composed of bunch of different types of molecules or atoms, and these molecules move very randomly with very high velocities, which means a gas consists of small particles, atoms or molecules that move randomly around the container, around the full volume of the container. Next, it tells us that the attractive force that is found between the particles of a gas is usually very small. So the force of attraction is really small, which means these particles are, the force of attraction to keep them together is really small. So they don't like to be closer to each other. Instead, they like to stay apart from each other. The actual volume occupied by the gas molecule is extremely small compared to the volume that the gas occupies. So basically, you can think of this, if you have these 5-6 molecules of gases and we put them together, they would probably fit into a space which is really tiny. Something like this. Whereas if we put it into a container and it's now a gas, these molecules will spread out very far apart from each other. So basically, gas would occupy much larger volume in comparison to their whole molecules. Next thing this theory tells us is that gas particles are always moving very rapidly. They are in constant motion and they are moving very fast around this container. The next thing this tells us is that the average kinetic energy of gas molecule is proportional to the Kelvin temperature. So we already know that temperature is an indicator of the energy, kinetic energy that is possessed by molecules. Higher the temperature, higher would be the kinetic energy. And in case of gases, whenever we talk about temperature, we usually talk about temperature in terms of or in units of Kelvin. So this theory also tells us the same thing, that the temperature is directly proportional to average kinetic energy of the molecule. That means higher the temperature, more kinetic energy the molecules have, the faster the particles are going to move around in their space. Next, whenever these molecules are in motion, they collide with each other. They also collide with the wall of the container or the surface of the container. And when they do that, they exert some kind of force or they exert some pressure on this container. And that pressure is basically called as the pressure of the gas. So every gas is going to exert some pressure when the molecules collide with the surface or the wall of the container. And those are basically all the properties or the behavior that is given by this model of kinetic molecular theory. Okay. Now moving on, talk about what are different properties of gas that can help you predict the behavior of the gas. The 4 major properties of a gas that can help us predict its behavior are pressure, volume, temperature, and the amount of the gas. So pressure of the gas, volume of the gas, temperature of a gas, and the amount of the gas basically dictates all the characteristics of a gas. Now let's take a look at all these properties separately. Pressure, what is pressure? By definition, whenever gas particles are moving around in a container, they collide with the surface of the container. And whenever they collide with the surface of container, they exert some force on the container, and this force per unit area is defined as pressure. Now, pressure of a gas can have multiple units. For instance, the units can be, here are some of the commonly used units for pressure. For instance, it's pascals, is usually abbreviated as capital P, small a. Kilopascals, which is essentially just another derivative of pascals. Then there is a commonly used unit which is atmosphere. Then there is millimeters of mercury or inches of mercury, torr, and pounds per square inch. So these are some commonly used units in pressure, and here you are given the conversion factors to go between different units of pressure. So all these conversion factors are, for instance, atmosphere is equal to 1 atm, and that is commonly said. So why? Because the atmosphere above the earth is basically, we only have one atmosphere above earth, and that atmosphere is exerting pressure on earth. So that pressure is usually regarded as 1 atm, and pascals is equal to 101325 atm. So basically you can regard this as 1 pascal is equal to these many atm. 1 kilopascal is equal to these many atm. So everything here is in reference to atmospheric pressure. So 1 millimeters of Hg is equal to 760 atm. So everything here is in correspondence to atm. 1 inch of mercury is 29.92 atm. 1 torr is equal to 760 atm, and 1 psi is equal to 14.7 atm. So this here everything is in reference to atmospheric pressure. So if you need to convert between any of these units, you could use these conversion factors. Now, how do we actually measure the pressure? So the device that is used to measure pressure is called a barometer. Okay, so what is happening basically on earth? There is pressure which is exerted by the column of air from top of the atmosphere to the surface of the earth, and that is referred to as the atmospheric pressure. And this atmospheric pressure is regarded as 1 atm at sea level. So basically if we try to go any deeper than the sea level, then this atmospheric pressure would increase, and if we go on higher altitudes, this pressure is going to decrease. Okay, now how does a barometer work in measuring this pressure? Basically you can assume that if we have this container filled up with mercury, now remember mercury is a liquid metal, it is really dense. If we fill this up with liquid mercury and then take a very thin capillary tube and invert it into this container, what would happen? The gases that are present in the atmosphere are going to exert pressure on this liquid mercury, which is open to air. And some of this liquid mercury, because of the pressure, is going to rise in this particular tube and reach a certain height. That height, when measured, is 760 millimeters of mercury. That is why another unit of pressure is given in millimeters of Hg. That means how much height of this mercury has risen when the pressure exerted onto liquid mercury is 1 atm. Okay, so barometer basically is a device that can be used to measure the pressure exerted by gases in atmosphere, and this indicates the atmospheric pressure as the height in millimeters of mercury column. Okay, all right, the next property is volume. You guys already are aware of volume from the previous chapters. What is volume? It's basically how much space is occupied by a substance, and in this case we are talking about gas, so the amount of space occupied by a gas would be referred to as its volume. Volume can be, the common units for volume of a gas can be liters, cubic centimeters, or milliliters. So these are some commonly used units for volume, and other units can also be used depending on what we are looking for. Only difference is if you need to convert, you should know the conversion factors between different units. The next property we saw was temperature, and as we discussed, temperature is basically a measure of the amount of heat or the amount of kinetic energy that is present in any substance. Here we are specifically talking about gases. Higher the temperature, faster the particles move because they have more energy. This temperature can be measured in different units. Remember, they can be measured in Fahrenheit, degree Celsius, or Kelvin. The important thing here is that whenever you're dealing with gases, always the unit of temperature that you would be using is Kelvin. Whenever you're working with gases, the only temperature that would help you predict the behavior of gas is if you work in temperatures of Kelvin. So here are the conversion factor that can be used to go from Kelvin to degree Celsius or degree Celsius to Kelvin. And if your temperature is given to you in Fahrenheit, basically you need to convert Fahrenheit into degree Celsius using this conversion factor, and then you can use the next conversion factor to go from degree Celsius to Kelvin. The important thing is to remember that the temperature that you're going to use, the unit of temperature in whenever working with gases should be Kelvin. All right, and the last property was the behavior of a gas would depend on how much gas we have. So the amount of gas, like we have discussed previously, the amount of gas is measured in moles. Any amount of substance in chemistry, the most commonly used unit would be moles. Alright, now let's see how these properties are related to each other and how can they help us predict the behavior of a gas. So all these properties are related to each other and their relationship has been given by different laws. So we'll go through all these laws first, one at a time. The first law was given by Robert Boyle and it's called the Boyle's law. This law tells us the relationship between pressure of a gas and volume of a gas when the other two factors are constant, meaning the relationship between pressure and volume when temperature and the amount of gas is constant. And what does this law tell you? This law tells you that the pressure of a gas is inversely proportional to its volume, meaning when the pressure increases, the volume of the gas decreases by the same factor. So for instance, if we have this particular jar with a pressure of 1 atm and the gas volume being 1 liter, and if I push this piston down now without changing the temperature and without changing the amount of the gas, what would happen? The pressure would increase. Let's say if I pushed this down and the pressure became 2 atm, what would happen to volume? The volume is going to decrease by the same factor. So if the pressure became double, the volume will become half. If the pressure was 2 times, the volume would become that over 2 divided by 2. And that's exactly what happens. If I increase the pressure over this gas, the pressure of the gas became 2 atm, which means now the new volume would be half of the initial volume. So pressure is inversely proportional to volume. This symbol that you're seeing right here in between the pressure and 1 over volume is called the proportionality symbol, which means as the pressure increases, the volume would decrease. Okay, and volume can also be expressed in this particular equation, which is called as P1V1 equals P2V2. Whenever you get a question to use this Boyle's law, only thing you have to make sure here that the units of P1 and P2 should be same and units of V1 and V2 should be same. Okay, here P1 and V1 are the pressure and volume of the initial amount of gas, the initial state that the gas is in, and P2 and V2 are the pressure and volume of the gas in the final state. Okay, so for instance, if I had a gas at pressure of 1 atm and a volume of 2 liters, and then the pressure was changed to 4 atm, what would be the new volume? So that way you can, if the question looks something like that, you could use Boyle's law to figure out what is the new volume of the gas under a different pressure. So how the question would look like is basically out of these 4, 3 of the conditions would be given to you and the question would be looking for one missing condition. Okay, only important thing is when using this formula, remember that unit of P1 and unit of P2 should be same. It could be atm, it could be pascal, it could be kilopascal, mmHg, it doesn't matter. As long as both of them are same, you're good. and same is true for volume. Okay, now if you were to make a plot of pressure versus volume, you know that if at pressure P1, which is a very high pressure, the volume is V1, and now I decrease the pressure to P2, meaning what would happen if I decrease the pressure? This volume would increase to V2. Therefore, your graph would look something like this. It would be more like a curve. Pressure and volume are inversely proportional. If I increase the pressure from P2 to P1, volume decreased. And if I were to make a plot of pressure versus 1 over volume, it would give me a straight line. Why? Because when I increase the pressure, what would happen to volume? Volume would decrease, but 1 over volume would increase. So let's say if this was my initial pressure and initial 1 over V, I increase the pressure. So pressure is high and volume is lower, but 1 over volume is also high. Therefore, my graph would look like a straight line. So these are the graphs for Boyle's law. Let's look at the next law. The next law was given by Charles. Therefore, it's called Charles' law. This law tells us the relationship between temperature and the volume of a gas when pressure is constant and amount of gas is constant. Okay, so out of the 4 properties, 2 of them are changing, whereas the other 2 are always constant. Okay. So if you think about this question, if we are not changing the amount of the gas and we are not changing the pressure of the gas, what would happen to a balloon? The volume of the balloon, if we increase the temperature of the gas, as we increase the temperature, gas is going to expand. The molecules are going to go away from each other, separate more from each other, and that's why volume is going to increase. So this law basically states that volume of a gas is directly proportional to temperature, meaning if the temperature is increased, the volume will increase by the same factor. And why is that? Because as we increase the temperature of a gas, now molecules have more kinetic energy, so they move even faster and they move away from each other. So therefore, the volume of the gas increases. Now, how can we this as a law? This is usually written as V1 over T1 equals V2 over T2, where V1 and T1 are volume and temperature of the initial state of gas, and V2 and T2 are volume and temperature of the final state of the gas. Again, the important thing here is that V1 and V2 should be in the same units of volume. T1 and T2 should be in the same units of temperature. And the next very crucial thing here is that remember to use temperature here in Kelvin. Temperature should always be in Kelvin. How would the graph look like for this? As the temperature, assuming this is the temperature, this is the volume. As the temperature has increased, the volume has also increased. As we increase the temperature, volume also increases. Therefore, the graph looks like a straight line. Okay, moving ahead, there's the next law, which is called the combined gas law. Combined gas law, just like the name states, if now I combine the Boyle's law and Charles' law together, that would give me combined gas law. This gas law basically can be written in this form. P1V1 over T1 is equal to P2V2 over T2. So you can see that this is a combination of the Boyle's and Charles' law. Boyle's law was P1V1 equal P2V2, and Charles' law was V1 over T1 equals V2 over T2. So this is basically a combination of the two laws. Therefore, it is called combined gas law. And what is constant here? The amount of the gas is constant in this scenario. The next law is called Avogadro's law. It was again given by Avogadro, and this law relates volume of a gas and the amount of the gas, where temperature and the pressure are constant. So if you have more gas, it will occupy more volume. That's exactly what this law tells us. Volume of a gas is directly proportional to the number of gas molecules, meaning as the amount of gas, or as the moles of the gas increases, volume of the gas also increases. Here n, here the small n stands for moles. This is an abbreviation very commonly used for moles. So as the moles increases, the volume of the gas would also increase. And if we were to write this law, it can be written as N1 over V1 equals N2 over V2. So this would be Avogadro's law. The next law is called as ideal gas law. This law is a combination of all the three laws that we saw before, which is Boyle's law, Charles' law, and Avogadro's law. If we combine all these laws, that would give us ideal gas law, which is also called as, which is written out as PV equals nRT. So here you can see pressure and volume are directly inversely proportional to each other, like Boyle's law gave us. Volume, if you rearrange this law, you can rewrite this as PV over NT equals R. So we saw that from Boyle's law, P times V equals a constant value from Boyle's law. We saw from Charles' law that V over T is a constant value from Charles' law, and V over N is a constant value from Avogadro's law. So basically, if you combine all these four factors in this particular way, it is going to be equal to a constant, and that constant is called as R, or is written out as R, and is called as the universal gas constant. And that's why if you rearrange this expression, it would give you ideal gas law, which is PV equals nRT. Now values of R could vary. For instance, R could have, it's a constant value, so it will always be constant. It never changes. Only thing it does is it depends on the units of pressure and volume. For instance, R could have a value of 0.08206 depending on the units of volume and pressure. If volume is liters, pressure is atm, temperature is Kelvin, and amount is in moles. R could also have a value of 8.314 when volume is in liters and pressure is in kilopascals. Temperature is in Kelvin and amount is in moles. So whenever you see a question based on ideal gas law, how would you decide which value of R to use? You are going to look for the units of pressure and volume. If whatever is the unit of pressure and volume, you are going to choose the same unit for R, and therefore it would have either one of these values. Okay, so these are all the gas laws that would help us predict the behavior of gas. Boyle's, Charles, Avogadro's, and ideal gas law. Also combined gas law if needed. Now let's see few questions. But what is important when you see a question, you should figure out what is given to you and what is the question asking. And then depending on what's given to you, you can figure out which law out of all the laws that we studied, which law you want to use. For instance, let's the first question. The first question says a balloon is put in a bell jar and the pressure is reduced from 782 torr to 0.5 atm. So the question is telling us this is pressure. The pressure is reduced from this. So this is the initial condition given to us, which is P1, to this, which means this is P2. If the volume of the balloon now is 2780 ml, what was it originally? So original volume means the initial volume, so that would be V1. The question is asking what is that, and it's telling us that now the volume is this much, so V2 is 2780 ml. So what is given to us in question? The question is giving us P1 of a gas, P2 of a gas, V1, V2 of a gas, and it's asking for V1. Now, do we know a relationship that relates pressure and volume? Boyle's law. Since the question has not talked about temperature and amount of the gas or moles, we can assume it is constant. Both of those values are constant. So now we can use, to solve for this question, we can use Boyle's law, which is P1 V1 equals P2 V2. We are solving for V1 right here, and what's given to us is P1, P2 and V2. All these three terms are given to us. If we are solving for V1, we need basically V1 on one side of this equal, and everything else should move on to the other side. So P1 has to be moved to the other side. To get rid of P1 here, since P1 is in multiplication of V1, if I divide this expression by P1, P1 and P1 will get cancelled. So I'm left with V1. But I cannot simply divide by P1 on one side of the equal. I have to do it on both sides of equal. So that would give me V1 is P2 V2 over P1. Now let's see if everything's given. P1 is given, what is the unit? Torr. P2 is given, what is the unit? ATM. Both the units of pressure are different, which means I have to convert them to same unit. You can convert torr to ATM or ATM to torr, does not matter. As long as both the units of pressure are same, we are okay. So now I will try to convert torr into ATM. You could also do the ATM into torr, doesn't matter. The conversion factor for that is given to you in the previous slide, which is 1 ATM equals 760 torr. So I will use this conversion factor to convert torr into ATM. How do I do that? I'll start with what's given, which is 782 torr. To cancel torr, I will divide by torr, multiply by ATM. 1 ATM from here is 760 torr, so 760 torr. Torr and torr got cancelled. My final P is 1.03 ATM. So this is P1. Now we can simply plug in the values here. P2 is 0.500 ATM times V2, which is 2780 ml, divided by P1, which is 1.03 ATM. Now before you work with numbers, cancel the units. ATM is cancelled. My final unit is ml, which makes sense for a unit of volume. If you plug this into your calculator, you would get 1350. How many sig figs are we looking for? This has 3, this has 3, this has 3. This 0 is not significant because there's no decimal. So 3 means I want final answer as 3 sig figs, and this has 3 since the 0 is not significant as there is no decimal here. So this is my final answer. You can also cross check your answer. How? What are we doing to the pressure here? The pressure was, initially the pressure was 1 ATM and it was finally reduced. If the pressure was reduced, the volume must have increased. So original volume would have been lesser. So you can see original volume is lesser than the final volume, which means we are probably on the right track. The solution for you is also given in slides. Look through those solutions. Let's try the next question. The next question is, a cylinder with a movable piston has a volume of 6 liters at 4 ATM. What is the volume at 1 ATM? So we again need to figure out what is initial, what is final. You can assume whichever one is initial here because it doesn't tell you what was the initial condition. So we'll assume that the cylinder has a volume of 6 liters. So I'll assume this is my initial volume is 6.0 liters. Initial pressure here was 4.0 ATM. What is the volume at 1 ATM? Meaning the pressure 2 is now 1.0 ATM. And what is the volume is the question. That's what I need to solve for. So what is the relationship again? This is between pressure and volume. So it is Boyle's law, P1 V1 equals P2 V2. Here I'm solving for V2. So to get rid of P2, I'll divide both the sides by P2. P2 get cancelled, which will give me V2 is equal to P1 P1 over P2. Okay, now simply plug in the values. Where is P1? P1 is in ATM, P2 is in ATM. Good. And V1 is right here. So we'll plug in the values. P1 is 4.0 ATM times 6.0 liters divided by P2, which is 1.0 ATM. ATM is cancelled. My final answer is in liters. If you plug this into calculator, it would give you 24 liters. I'm looking for how many sig figs. This has 2, this has 2, this has 2. My final answer is 2. So this is my final answer. Okay, the next question is right here. A gas has a volume of 2.57 liters at 0 degrees Celsius. What was the temperature at 2.80 liters? So what's given to us is the volume of a gas at 0 degrees Celsius. So I will assume this is my initial volume. So initial volume is given to me as 2.57 liters. What's given to me is temperature right here. So initial temperature, meaning T1, is 0 degree Celsius. What was the temperature at 2.80 liter? Liter means this is volume. So this is the final volume, 2.80 liters. The question is, what is T2? All right. So here, nothing has been talked about pressure or amount of the gas, so we'll assume those are constant. The relationship here is between volume and temperature. So what is the law that dictates this? This is based on Charles' law, which is V1 over T1 equals V2 over T2. Here I'm solving for T2, so we'll rearrange the equation in a way so that I can get T2 here. How would I do that? I would basically, if I divide both the sides by V2, that would give me V2 is cancelled, and now I'm left with 1 over T2. So in order to get T2, I need to do inverse of this. So that means T2 here, if I take inverse of that, this side will also get inversed or reversed. That would give me V2 times T1 over V1. Okay, so now we can simply plug these values into our calculator. Do we have V2 given to us? Yes, it is in liters. V1 is also in liters, so we are good. But T1 here is in degrees Celsius. Remember, temperature always has to be in Kelvin. So I will have to convert this temperature to Kelvin. What is the conversion factor? Temperature in Kelvin is equal to temperature in degrees Celsius plus 273. So whatever is the temperature in degrees Celsius, add 273 to that. So 0 plus 273 will give me 273 Kelvin. So if I plug this now into this equation, T2 will be V2, which is 2.80 liters, times T1, which is 273 Kelvin, divided by V1, which is that would be 2.57 liters. So here liters and liters will get cancelled. Our final answer is in Kelvin, which is a unit for temperature. Now let's plug all of these values into calculator. That would be 2.80 times 273 divided by 2.57, which is 297.43 Kelvin. Now how many sig figs am I looking for? 1, 2, 3, 1, 2, 3. So that would give me my final answer as 1, 2, 3, which is 297 Kelvin. All right, so that is our final answer for temperature. All right, So you could find the solution in this slide as well. Let's continue to the next question. This question tells us that the temperature inside a balloon is raised from 25 degrees Celsius to 250 degrees Celsius. So basically this was my initial temperature. T1 was 25.0 degrees Celsius. T2 is 250 degrees Celsius. If the volume of cold air was 10 liters, what is the volume of hot air? So cold air would be this, which means it's talking about, if this is 1, volume would also have to be 1. V1 is, I would rewrite it here. V1 is 10.0 liters. The question is asking what is V2. So again, this is based on a relationship between volume and temperature. There is no pressure, there is no amount of gas, which means we can use Charles' law. V1 over T1 is V1 over T1 is equal to V2 over T2. Here we are solving for V2, so we need to bring T2 on the other side. So if I multiply by T2 on this side and on the other side, T2 and T2 gets cancelled. I'm left with V2, which would essentially be V2 equals V1 times T2 over T1. V1 is given to us in question. T1 is given to us in question. T2 is given to us in question. But both the units are in degrees Celsius. So I will be adding 273 to each of them to get my final temperature. So this would be 298 Kelvin. And the T2 is going to be 523 Kelvin. Now we simply plug all the values into this equation, which is V1 is 10.0 liters times T2, which is 523 Kelvin, divided by T1, which is 298 Kelvin. Kelvin got cancelled. My final unit is liters, which is a unit for volume. If you plug all this into calculator, it would give you 17.5 liters. I'm looking for 3 sig figs in my final answer. So 3 sig figs from here, 25.0. This is 4, but eventually I want 3 sig figs because of 10 liters, the least amount of sig figs. So this is also 3 sig figs. So this is my final answer. Okay, let's try another question. Okay, a sample of gas has an initial volume of 158 ml at a pressure of 735 mm of Hg and temperature of 34 degrees Celsius. So this is given to us: initial volume, initial pressure, initial temperature. So V1 is given to us. V1 is 158 ml. P1 is 735 mm of Hg, and T1 is 34 degrees Celsius. The question is, if the gas is compressed to 108 ml and heated to 85 degrees Celsius, what is the final pressure? So question is asking what is P2, what is the final pressure if the gas is heated to, meaning T2 is 85 degrees Celsius and is compressed to 108. So V2 is 108 ml. So question is what is P2. Now here 3 different parameters are given to us, and what is constant is amount of gas, which means the law that dictates this is combined gas law. P1 V1 over T1 equals P2 V2 over T2. What are we solving for? P2, which means we need to get rid of V2 and T2 from here. How can I do that? V2 is in multiplication, so if I divide by V2, this will get cancelled. T2 is in division here, so if I multiply by T2, T2 will get cancelled. And I do the exact same thing here, multiply by T2, divide by V2. This and this, this and this got cancelled. I'm left with P2. So my relationship now is P2 is equal to P1 V1 times T2 divided by V2 times T1. Now we simply have to plug the values into this equation. Do we have P1? Yes. Do we have V1 and V2? V1 and V2 right here, same unit, which is good. T1 and T2 are right here, but the units are in degree Celsius. So I need to convert this into Kelvin by adding 273. So T1 will become equal to 307 Kelvin and T2 will become equal to 358 Kelvin. Now we plug all these values into this expression, which will give us P2 equals 735 millimeters of Hg times V1, which is 158 ml, times T2, which is 358 Kelvin. Don't make a mistake when plugging in your numbers. Just look for what exactly you're looking for. I'm looking for T2. T2 is this. Divided by V2, which is 108 ml, times T1, which is 307 Kelvin. So now cancel units first. This would make ml and ml cancelled, Kelvin and Kelvin cancelled. I am left with mm of Hg, which is a unit for pressure. So that is good. This, if you plug into calculator, would give you P2 as 1.25 times 10 raised to power 3 mm of Hg. So I'm looking for 3 sig figs. 3 right here. You can see 3, 3, 3. All of these are 3 sig figs. So my final, these are also 3 sig figs. My final answer is 3 sig figs. Okay. Moving on to the next type of question you can expect. Right here, a gas occupies 10 liter when its pressure is 3 atm and temperature is 27 degrees Celsius. What volume will the gas occupy under standard conditions? So we have not talked about standard conditions yet. So let's first talk about what are exactly standard conditions, and then we can walk through this question again. Okay. So skip this question for now. And we'll move to the next question for now. Okay. And then we'll come back to this question later on. The next question is a 0.22 mole sample of helium has a volume of 4.8 liters. How many moles must be added to give 6.4 liters of helium? So what's given to us is that a 0.22 mole of sample of helium has a volume of this much. So basically I can assume this is my initial condition and this is moles, so I'm talking about N. N is 0.22 moles. Volume is V1, which is given to us as 4.8 liters. And the question is asking how many moles are added. Moles added to 0.22. What is the final volume? 6.4 liters. So you can clearly see based off of this, it's a relationship between volume and number of moles, which is Avogadro's law, which is N1 over V1 equals N2 over V2. N1 is given to us, V1 is given, V2 is given. I'm solving for N2, not directly, but the question is asking how many moles were added. To figure that out, the only information I can figure out based on the laws that I know is what is the final moles. So if I know the final moles, I can take difference of final and initial moles, and that would tell me how much more moles were added. Okay. So now if I'm solving for N2, I would multiply both the sides by V2. So V2 and V2 will get cancelled. and I will be left with N2. So my relationship is N2 is N1 times V2 over V1. If we plug this into calculator, N1 is 0.22 moles times V2, which is 6.4 liters, divided by V1, which is 4.8 liters. So liter and liter cancelled. My final answer is in moles. How many moles? If you plug this into calculator, that would give you 0.29 moles. 2 sig figs, 2, 2, 2. So answer is 2. But this is not the final answer. The question is not asking what is the final number of moles. It's asking how many extra moles were added. So the number of moles that were added would be equal to final minus initial. So 0.29 mole minus 0.22 moles, which would give us 0.07 moles, which is 2 decimal places. This is 2, this is 2. My final answer is 2 decimal places. So this is my final answer. Okay. All right. Let's move on to the next type of question you can expect, which is this. So the pressure of a gas in a 2500 ml container is this much at 28 degrees Celsius. Calculate the number of molecules of the gas present in the container. So what is given to us? Volume of a gas is given 2500 ml. Pressure of a gas is given 0.500 atm, and temperature of the gas is given 28 degrees Celsius. Question is asking what is number of molecules of the gas. Now you can see from the question we are not changing volume, we are not changing pressure or temperature. So this is not, we are not doing 1 and 2 here. There are no 2 states here. Initial state and final state does not exist here. It's only one state. So what is happening here? Volume is given, pressure, temperature is given. The question is asking what is the number of molecules. Do we know a relationship that relates volume, pressure, temperature, and amount of gas? Ideal gas law. We know that PV equals nRT. Pressure is given, volume is given, temperature is given, and R is a constant which we already know. So that's, you can assume that is given. What's not given is N. N is the moles. If I can solve for N from here, I can figure out moles. Once I know moles, I can simply convert moles into molecules by using the conversion factor, which is Avogadro's law. So 1 mole will be equal to 6.02 times 10 raised to power 23 molecules. So that would be my solution map. Use this equation first, which is ideal gas law, then use moles to molecules. So now let's see what can we use for ideal gas law. Pressure is given 0.5 atm, volume is given PV equals nRT. I am solving for N, so N will be equal to PV divided by RT. Pressure is given in atm, volume is given in ml. Missing information here is R. So now you know R has different units, where one is pressure is atm or kilopascal. I have a conversion factor which is in atm. I have a value of R in atm, so I can write that value right here, 0.08206 liter atm Kelvin inverse mole inverse. Okay, so now atm is pressure, good. Temperature is degrees Celsius. Here temperature is Kelvin, so I need to convert this into Kelvin by adding 273. If you add that, it would give you a temperature of 301 Kelvin. Next, you see volume is in liters. So what's given to me is ml. So I will have to use the conversion factor to go from ml to liters, which is ml is 1000 ml is equal to 1 liter. So you begin with what's given, which is 2500 ml. I'll cancel the ml, convert to liter. 1 liter is 1000 ml. ml cancelled. My final answer is in liter, which is 2.500 liters. Okay, or actually it would be 2.5 liters. Why? Because 2500 has how many sig figs? 1, 2. So my final answer should have 2 sig figs here. Okay, now I have volume in the right unit, pressure in the right unit, temperature in the right unit, and R in the right unit. So we plug those values in. Pressure is 0.500 atm. Volume is 2.5 liters. Temperature is 301 K and R is 0.08206 liter atm divided by Kelvin mole. Per mole means divided. So Kelvin and Kelvin cancelled, atm cancelled, liter cancelled. I am left with a unit of 1 over mole. So 1 over mole means reverse of 1 over mole, which would give me mole. So the final unit that I'm getting here is moles. If you plug all of this into calculator, you would get 0.05 moles. Okay, how many sig figs am I looking for? This has 3, this has 3, this has 2. So I want 2 sig figs in my final answer, which means I'll add a 0 right here. So now it has 2. So this would be my final answer. Okay, there is another that is given to you in this worksheet that you could practice on your own. The solution, which is right here. Calculate the volume occupied by 637 grams of SO2 gas at this much of millimeters of Hg and minus 23 degree Celsius. So let's write what's given to us in question. The question is giving me mass of the gas. It is telling me I have 637 grams of gas. Grams is mass. Then it's giving me millimeters of Hg, which means this is pressure. 6.08 times 10 raised to power 3 millimeters of Hg. Then temperature is given to us minus 23 degrees Celsius, and the question is asking what is volume of the gas. So again, pressure, temperature, volume, they are not changing, so it is not Boyle's, Charles, Avogadro's, or combined gas law. Only law that's left is ideal gas law. And what does that law tell us? That law tells us that PV equals nRT. If I need to solve for volume, I need to get, I can rearrange it as nRT over P. Do I have T given to me? Yes. It's degrees Celsius, but I can convert. Do I have P given to me? Yes. Do I have R given to me? R is a constant which is always given. Do I have N given to me? No. So I need to find N. Is there any way from here, the information that is given to me in question, any way can I find N from here? N is number of moles. Yes. How? What's given to me is grams of the gas. And grams of the gas can be converted into moles of the gas. How? The relationship that goes from grams to moles is molar mass. So grams of SO2 to moles of SO2 would be molar mass, which is given to you in question, mm. So 1 mole of SO2 will be 64.07 grams of SO2. If I start with what's given, which is grams, 637 grams. To cancel gram, I divide by grams of SO2, multiply by mole of SO2. Mole is 1, gram is 64.07. Gram and gram is cancelled. I'm left with moles of SO2, which will come out to be 9.94 moles of SO2. Now we can simply plug all the values in here. But first, let's see what is the unit of P. P is in mmHg. Pressure is in mm of Hg. The only units of R that we know are either in atm or the pressure is in kilopascals. So what we can do is we'll have to convert the unit of pressure to either one of these. So I'll go with the unit of atm. You can choose whichever unit you want. So let's convert here pressure from mm of Hg to atm. The conversion factor that we can use is mm of Hg to atm. The conversion factor is 1 atm equals 760 mm of Hg. So we start with mm, which is 6.08 times 10 raised to power 3 mm of Hg. We divide by mm and multiply by atm. 1 atm 760 mm. If you cancel this, mmHg cancel, our final unit of pressure is atm, which comes out to be 8 atmospheres. So it would be 8.00 atm. This is our pressure now. Now we can plug all the values in. What is the value of R at this state? R is, again you can look through your slides, it would give you 0.0821 liter atm over Kelvin moles. And temperature is minus 23 degrees Celsius, so we convert it into Kelvin. That would give us a temperature of 250 Kelvin. Now we plug everything into this expression. Now I also have number of moles, so I can simply plug everything here, which will come out to be V equals N is 9.94 moles, R is 0.0821 liter atm over Kelvin mole, temperature is 250 Kelvin, and pressure is in atm 8.00 atm. So now let's cancel units first. Mole, mole, Kelvin, Kelvin cancelled, atm, atm cancelled. So I'm only left with liters, which is a unit of volume. So which means I'm probably on the right direction. So the answer will come out to be 25.5 liters. That is the final volume that it would be occupied by this gas under these conditions. Next, let's move on to the next concept of this chapter, which is the standard temperature and pressure conditions. So there could be multiple temperatures and multiple pressures that are possible. Therefore, scientists came up with a term which is called STP, which stands for standard temperature and pressure. Here, the temperature is always assumed to be the standard temperature by definition is 0 degrees Celsius or 273 Kelvin. This is to avoid any kind of confusion when we change temperature and pressure. We can basically figure out what is the property of gas at a certain temperature and pressure, which is standard, and then use that to predict how the gas would behave if we change any of these properties of the gas. Okay, so therefore standard temperature is at 0 degrees Celsius 273 Kelvin, and standard pressure is always fixed at 1 atm or 760 mm of Hg. Now if you were to calculate what is the volume of the gas, what is the volume occupied by a gas, which is 1 mole at standard temperature and pressure condition. Okay, the question is this, which is calculate the volume occupied by 1 mole of an ideal gas at standard temperature and pressure conditions. So what is the volume at STP? Meaning amount of gas is given as 1 mole, which is N, So N is given. Question is asking what is volume at STP. STP means temperature is also given to us, which is 273 Kelvin, and pressure is also given to us, which is 1 atm. So P is given, T is given, N is given. Question is asking V, which means we can use PV equals nRT here, right? And I am solving for V. So V will be nRT over P. If I plug everything in, N is 1.00 moles, R is 0.0821 liter atm over mole Kelvin. Temperature is 273 Kelvin divided by pressure, which is 1.00 atm. So atm cancel, Kelvin cancel, mole cancel. Our final answer is in liters, which always comes out to be 22.4 liters. Always. For any gas, any 1 mole of a gas at STP will always occupy 22.4 liters, irrespective of what gas it is. Okay, any gas at STP, 1 mole of that gas will always occupy 22.4 liters. Okay. Therefore, this is also sometimes referred to as molar volume, meaning the volume occupied by 1 mole of a gas is called molar volume. So you could use this as a conversion factor now, which means 1 mole of a gas only at STP is equal to 22.4 liters. So this is your conversion factor to go between moles and liters of gas if needed, but only at STP. Right? The next thing is absolute zero. So absolute zero is basically a temperature where a gas would have zero volume and zero pressure. This temperature is called as absolute zero, meaning it is equal to 0 Kelvin. 0 Kelvin would be in degree Celsius would be negative 273 degrees Celsius, and Kelvin it would be negative 459 degree Fahrenheit. Sorry, not Kelvin. The 0 Kelvin would be minus 459, almost 500 degree Fahrenheit. This temperature is never attainable. It is so low that it can never be attained. We can never reach close to this temperature. If we do reach close to that temperature, that means everything, gas will have no volume, no pressure, which means basically the world is not existing. Nothing is going to behave like normal. Okay, so this temperature is so low that it cannot be attained. Okay, so this is called the temperature of absolute zero. Exist. So now, based on the molar volume that we saw, any gas, irrespective of which gas we are talking about, 1 mole of the gas would be always 22.4 liters. So if you have a balloon filled up with 1 mole of helium at STP, which is 273 Kelvin, 1 atm, it will occupy a volume of 22.4 liter. If you replace helium with oxygen, same condition, 22.4 liter. If it is nitrogen, same condition, it is still 22.4 liter. So irrespective of which gas we are talking about, at STP, each gas will occupy a volume of 22.4 liters. Okay, how can a question be asked on this information? Like this. What is the volume occupied by 2.75 moles of nitrogen gas at STP? So the question is asking what is the volume occupied by 2.75 moles of nitrogen. So N is given to us, 2.75 moles at STP. One easy way to do this is, we know the relationship. The question is asking to go from moles to volume, which is liters, assuming. Okay, volume, I would assume it is asking it in liters. So one easy relationship now we know is that 1 mole of a gas will always occupy 22.4 liters. So you could use this. We start with what is given, 2.75 moles. To cancel mole, I divide by mole, multiply by liters. 1 mole is 22.4 liters. So mole and mole is cancelled. My final answer is in liters. Okay, one way is that this would give you, if you plug this into your calculator, this would give you 22.4 times 2.75 is 61.6 liters, 36. But another way, if you can't remember this, you could also do PV equals nRT. Here what's given to you is N, R is already known, STP means temperature is 273 and Kelvin, and pressure is 1 atm. So all the values are given except for volume. If you want, you could also use this to figure out the final answer. Okay. What is the volume at STP of 4 gram of CH4? So what is the volume occupied by 4 grams of gas at STP? We know that 1 mole of gas occupies 22.4 liter. So I know that 1 mole of a gas will occupy 22.4 liters of a gas. Okay, but here the question is asking from grams to liters. So what is the conversion factor there? I'll first have to go, only relationship I know right now is from moles to liters. So basically that means I will first have to go from grams of the gas to moles of the gas, and then I can go from moles of the gas to liters of the gas by using this conversion factor. And the conversion factor to go between grams and moles would be molar mass. For molar mass, you look up your periodic table. Carbon is 1 atom, so 12.01 grams of carbon, plus 4 atoms of hydrogen, so 4 times 1.01 grams of hydrogen. If you plug this all into calculator, this would give you 16.05 grams of CH4. Okay, so the conversion factor is 1 mole of CH4 is 16.05 grams. Now we start with what's given, which is 4.00 grams, divided by grams multiplied by moles. 1 mole 16.05 gram. Gram cancelled. I am right here with moles. Now I can convert moles to liters by dividing by mole, multiplying by liters. 1 mole 22.4 liters. So now if you plug this into your calculator, your final answer is going to be 4.00 divided by 16.05 times 22.4. I am getting the final answer as 5.582 liters. I am looking for 1, 2, 3 sig figs, which would give me 5.58 liters as my final answer, which is very close to this 5.60. Right. Next, the question is, how many grams of helium are present in 8 liters of a gas? So now the question is asking me to go from liters to grams of a gas at STP. So what do I know about gases at STP? I know again that I cannot directly go from liters to grams, but what can I do? I can simply go from liters to moles, and then I can convert moles to grams. So liters to moles would be again 1 mole is equal to 22.4 liters, and mole to grams would be 1 mole is equal to molar mass of helium, which is 4.00 grams. So you could use these conversion factors to go from liters to grams. Okay, and I'll let you guys figure this question out on your own. I've basically drawn the solution map from you. Now you start from liters, cancel the units by using these two conversion factors, and get to grams. The last topic to be covered in this chapter of gases is called Dalton's law of partial pressure. Okay, what does this law tell us? This law essentially tells us that assume you have a balloon filled up with some hydrogen gas, a certain amount of helium, certain amount of nitrogen, certain amount of oxygen gas. What would be the total pressure exerted on the balloon? The total pressure exerted would consist of some pressure exerted by helium, some by nitrogen, some by oxygen, some by hydrogen. So Dalton law tells us that the total pressure exerted by the gas in a mixture is sum of the partial pressures exerted by all the gases that are present in the mixture. So basically, if I have some hydrogen gas there would be some pressure by hydrogen, some pressure by oxygen, and some pressure by nitrogen. So total pressure, T stands here for total. So total pressure exerted by all the gases in there would be a sum of the pressure exerted by individual gases. And that pressure which is exerted by individual gases is referred to as the partial pressure of each gas. So this is partial pressure of hydrogen, partial pressure of oxygen, partial pressure of nitrogen. And the total pressure is sum of all of these. So this is Dalton's law of partial pressures. How would the question look like? Simple. Like this. A mixture of helium, neon, and argon has a total pressure of 558 mm Hg. So what's given to us is total pressure 558 mm of Hg. If the partial pressure of helium is 341 mm Hg, partial pressure of neon is 112 mm Hg, determine the partial pressure of argon. Okay, so now we know that total pressure is equal to pressure of argon plus pressure of helium plus pressure of neon. This is given, this is given, this is given. Question is asking for argon. If you rearrange this, you would get pressure of argon as pressure total minus pressure of helium plus pressure of neon. So you simply plug the values in here and figure out what is the pressure of argon. Only important thing here again is that all your units should be same. So you can see everything is in mm of Hg. So we are okay. Plug the values in. So P of argon would be total pressure, which is 558 mm of Hg, minus pressure of helium, which is 341 mm of Hg, plus the pressure of neon, which is 112 mm Hg. If you plug these values into calculator, it would give you 105 mm of Hg. Again, 3 sig figs in our final answer is what we are looking for. So this is the final pressure which is exerted by the partial pressure which is exerted by argon gas. And now one last topic that I want to discuss here is about vapor pressure of a gas and its boiling point. So basically any gas, any liquid, if we have a beaker filled up with a liquid, every liquid, and I close this container, at any given temperature, some of this liquid will turn into gas, which is turned into vapor molecules. So most of this will be going to be liquid right here. Most of them will be liquid, but some of them will convert into vapor. And this vapor, this gas that is present on top of the liquid, will exert some pressure onto this liquid, and this pressure is called as the vapor pressure. Okay, and what is the principle behind a liquid turning into Steam, or the process of boiling, what happens in boiling? Basically, if there is a liquid right here, it has bunch of molecules, they have some energy, they are moving around. When we heat these molecules, some of these molecules will gain a lot of kinetic energy, and they will try to break all the forces of attractive forces that they have within the molecules, between these different molecules, and it will break away from the liquid and it will turn into vapor. And that is the process of boiling. So now, if the vapor pressure is higher on the gas, that means the gas molecules are trying to stay closer. If there is a higher vapor pressure, when would that happen? When a higher vapor pressure, when these gas molecules are very separated from each other. Okay, so if a liquid, if in case of a liquid, all these molecules have very weak force of attraction that is keeping them together, that means these molecules will easily turn into gas, and that gas will exert vapor pressure, which means higher the vapor pressure exerted by a liquid, lesser or weaker would be the force of attraction. Okay, lesser force of attraction means lower would be the boiling point. What that means is, if we have a liquid here which has certain molecules that have very weak force of attraction with each other, what would happen? They can easily break apart from each other and turn into gas. And when they turn into gas, that is called the boiling point. The temperature when they turn into gas is called the boiling point. So they can easily get to that temperature and break away. Okay, and when does this happen? When do things start to boil? There is always, if it's an open container, there is always atmospheric pressure being exerted from atmosphere by the air that is present on top. So if the atmosphere is exerting pressure, what that means, that these molecules are being pushed into the liquid, right? But whenever these molecules have enough energy to break apart from or break away from this atmospheric pressure, that is when these liquids start to boil. So whenever the vapor pressure basically becomes, at a given temperature, becomes equal to the external pressure, meaning 1 atmosphere, if it is open to air, that's when things start to boil. Whenever the vapor pressure become equal to external pressure, this liquid will start to boil. So that's why when water boils at sea level, at the normal plane on land, usually it boils at 100 degrees Celsius. Okay, which means the temperature, at the temperature of 100 degrees Celsius, the vapor pressure of water becomes equal to 1 atmosphere, right? But when this water is at, let's say, a higher altitude, the water boils much more easily at a much lower temperature. Why? Because the atmospheric pressure there is lesser. Instead of 1 atm, maybe it is 0.95 atm. So now the vapor pressure only has to become, instead of becoming equal to 1, it has to become equal to 0.95, which is easier, which can be attained at a lower temperature. So there water boils at a much lower temperature, right? So that is how vapor pressure is associated. So at higher altitudes, atmospheric pressure is less than or lower than 1 atm. Therefore, boiling of water occurs at a lower temperature than 100 degrees Celsius. So this explains how gases behave, what is vapor pressure, and how liquids boil at different pressure conditions. Okay, so this is the end of this particular chapter of gases.